So we can just jump right in here. I got a question last time, and I just wanted to walk back and just make sure that everyone kind of was on the same grounds about electromagnetic radiation and energy radiated balance, because it's important to understand climate change, because it's essentially the foundation of why the climate is changing. And not everyone might have the same kind of physical background. So this is something that I presented last time. It's the radiative energy balance. It's a conceptual model with some numbers attached, and it shows the incoming solar radiation. So that's photons from the sun, typically of a higher wavelength, so more energetic. They come in, they bounce off the atmosphere, they go down, they do, work in plants, or they heat up the ground or whatever. They evaporate water, and then the earth gets warm from the sun, and everything that's warm glows a little bit. Let me pull up this graph here. Everything that's warm glows a little bit according to the rules of Blackbody radiation. So you may not know, but you're all glowing right now. You're all releasing photons in the form of infrared radiation. Infrared radiation and are carried by photons. And the hotter you are, or the hotter an object is, the brighter it glows, and the more intense the radiation that comes off of it. So the amount of radiation, which is displayed here, radiation intensity on the y-axis, and the wavelength of the radiation on the x-axis. So these particles up here, this radiation is very high energy. It's very small wavelength, which means that it can get into your cells, it can break up your DNA, it can cause genetic damage. And that's the kind of stuff that you want to block from entering the planet through things like ozone, the ozone layer in the atmosphere. But anyway, I just wanted to take a step back and kind of mention this, because I didn't mention last time that the Earth glows, and that glow is the energy out. But you just can't see it, because it's not visible light, it's infrared light and lower wavelengths like radio waves. So we can, I was just going to, I forgot I put in this little video, but this is the glowing filament of a light bulb, and this is demonstrating blackbody radiation. So you run an electric current through a filament, and the electrons aren't able to pass very easily through that filament, because it's like dense metal or carbon or something like that, and so they hit the atoms inside the filament and they cause them to heat up. And as they heat up, they release photons. They glow due to this relationship here, and that's what makes all the light come out of the light bulbs. Anyway, and then we also last time went over the writing assignment, and if anybody had any questions about that, we could talk about that now as well. But if not, we could move forward. So today, finally, we're going to be talking about the current impacts of climate change a little bit, and also mostly the predicted future impacts of climate change. And we're also going to be talking about how we can make those predictions. And so we'll go through all of these things, but basically, the planet's getting hotter, and that causes changes in rainfall patterns, and cold days, and warm days, and melting of the ice caps, sea level rise, et cetera, et cetera, et cetera. And it would be impossible for me to give you a complete overview of every single impact of climate change, because it affects essentially every single thing on the surface of the Earth and in the oceans. And that's just too much to cover in an hour and a half. But what I want to do is I want to give you kind of the high-level picture of the major impacts, so that you can, in the course of thinking about different things for your writing assignments or whatever, you can kind of picture how, say, sea level rise and the melting of the permafrost would, could affect Inuit tribes in Alaska, for example. So anyway, speaking of, I wanted to give some recent examples of climate change in action. So obviously we all are familiar with the fires that have been going on in California. Those are inextricably linked to climate change, from the droughts that have happened. The trees are very heat stressed, they're water stressed, and that makes them more vulnerable to diseases and pests like bark beetle. And so they die, and when they die, they make perfect fuel for more intense wildfires, and we kind of talked about that last time. We're also going to see with increased precipitation, increased evaporation leads to increased precipitation, and then that gives you bigger, stronger storms. And so, for instance, Hurricane Ophelia hit Ireland in 2017, October 2017, and killed people. I mean, a hurricane in Ireland, when did you ever hear about that? You haven't, because it hasn't happened in recorded history. And then, of course, Hurricane Maria, and I'll show a little clip of some of the aftermath that's still going on. And it's not just the physical impact of these major storms on Puerto Rico or Houston or wherever. It's our response to that as well. And the infrastructure that we have in place to counter that is very revealing about what types of socioeconomic impacts that climate change will have. And then finally, we'll show a little bit about some of the flooding in the Midwest. I mentioned last time that this class was supposed to have 2 TAs, and one of them is out in the Pine Ridge Reservation right now, dealing with the flooding and coordinating with the local leaders out there to get FEMA in, because they're not recognizing it as an emergency, the Trump administration. So this is just a quick video. I wanted to, because we're going to be talking about a lot of high-level stuff, a lot of charts and graphs, that they're pretty dry. So I want to, because climate change is real and it's not an abstract thing like we talked about last time, I wanted to, let it kind of hit home. So these are people's experience with climate change. This is the fire. This is the California fire. Oop.
Heavenly Father, please help us. Please help us to be safe. I am thankful for Jeremy and his willingness to be brave.
And it's a sunny day. So climate change is not just graphs and figures. It's your hometown burning down. It's driving through blazing infernos and not knowing if the place that you're going to is going to burn down next. And it's also not knowing what's going to happen to the infrastructure of the place that you live. I mean, look at I don't know why it's not working. I mean, look at PG&E. PG&E has been driven to bankruptcy by these fires because they haven't, and they've acknowledged that they are running the risk more and more each year of starting fires because of climate change. The CEO, well, the former CEO, she got kicked out, the former CEO of PG&E, after these fires happened, she admitted that it was climate change. She was trying to kind of blame it, on climate change, but really, we've all known this is coming. And the fact that PG&E hasn't upgraded their infrastructure in accordance to the increased threat level that they were aware of, is still their liability. And so, it's affecting the very, the new governor, Governor Newsom, came in and his first thing that he did was try to deal with these wildfires. It's completely taken over the politics of the state. It's taken over a lot of, the media discussion in the state right now. So, and this was one wildfire season. And it's had major impacts, in places like Forbes, which you can't see because this has got cut off for some reason. Places like Forbes and Business Insider are saying climate change has caused PG&E to go bankrupt. These are not like liberal fantasy, media outlets. These are like mainstream business outlets saying climate change caused the company to go bankrupt. And speaking of bankruptcy, morally and otherwise, here's the aftermath of Hurricane Maria.
Senator Bill Nelson met with Puerto Rican residents who were displaced from their homes after Hurricane Maria. The group was on Capitol Hill today urging lawmakers to do more to provide affordable housing to thousands of families affected by the storm, many of them ending up here in the state of Florida. Hurricane Maria was a Category 4 storm when it made landfall in Puerto Rico last September, plunging the island into a humanitarian crisis.
And then we went outside, and it was, devastation. It was like a bomb was, there.
When the storm hit, Vivian Rivera was in the town of Comerío in the mountainous central part of the island. Her hometown was left unrecognizable by hurricane-force winds and torrential rains that turned streams into raging rivers.
We just decided to take a walk. me and my cousin, and we cried all the way. I mean, it was
Maria was the worst natural disaster ever to hit the U.S. territory. The storm knocked down 80% of the island's power transmission lines. Millions were left with no electricity, cell phone service, medicine, food, or water.
We didn't have any water, we didn't have any electricity, so we didn't have a way to communicate with police, our family. I mean, there were no phones, no way to go in the car anywhere because the roads were blocked with, you know, the mudslide, the trees, and the electric poles.
Getting aid to the island proved challenging, but getting the aid out of the capital of San Juan was an almost insurmountable obstacle, leaving Puerto Ricans out of touch with the rest of the world and feeling hopeless and forgotten.
It was really scary. It was like we were in another place, you know, like isolated.
Maria forced thousands of Puerto Ricans to leave for places like Florida. Vivian lives in Hollywood, but her 89-year-old mother, Rosa, remains in Puerto Rico, as do other family members who are still dealing with power outages and water shortages.
Some days they get up in the morning and they don't have electricity, so the whole day without electricity, they lose the groceries and stuff, and then the next day they do have electricity, but they don't have water. So it's like a day by day thing, you know.
Vivian shudders to think what a new hurricane season will bring to Puerto Rico.
If another hurricane comes, I mean, it's going to be gone again.
Now, 8 months after Hurricane Maria hit Puerto Rico, the death toll remains a real mystery. The official count of deaths on the U.S. territory stands at 64, but a recent Harvard survey says it's more than 4,600. And guys, the government of Puerto Rico is doing a study. George Washington University is heading it to really come up with a definitive number.
And it's just so scary to think that we're in hurricane season again right now, as they're still trying to recover from last year.
That's going to be very difficult. Wow.
So I let it play a little bit at the end there just so that they would bring up the thing about the death toll, because the official count, as they said, is super low. And the real count is, I'm sure, higher than the number that they gave, because, it's tricky to account for all those deaths. Did you die of a disease that you caught from, some sewage that came out during the flooding? Did you die, during the hurricane, did something hit you in the head? And they also mentioned in the video that, it's not just one hurricane, it's the next hurricane and the next one. And, how do we deal with the overlapping recovery times, as these things become more frequent? And this is the official Trump response to the Hurricane Maria. Hucking paper towels at people's heads. Just because I wouldn't have believed it if I hadn't seen it with my own eyes. This is the President of the United States. I don't even want to watch all that. This is the flooding in in the Lakota Nation right now. So this is a video that we just made, that Chris made, and it just shows a little bit of the flooding that's happened, because it's not really being covered too much.
Giant rivers, heavy rain and snow melt have sent rivers over levees, submerging a thunderstorm described by meteorologists as a bomb cyclone is blasting parts of the country's midsection. Powerful winds combined with snow are creating blizzard conditions.
Floodwaters showed little sign of dropping off here on Pine Ridge as tribal authorities and outside agencies strive to help community members in distress.
This flood has done tremendous damage to our public infrastructure. More than 1,000 of our families were displaced.
On March 29th, South Dakota Senate passed SR 7, urging President Trump to declare South Dakota, the counties that were impacted and the tribes that were impacted, a disaster area. During this time, the tribe has depleted all resources, so we're looking for donations, anything that could help communities addressing immediate needs.
So we need people to come here, accountants, bookkeepers, engineers, anybody who has experience, especially with disaster declarations. We need to get a disaster declared. We are seeking all the assistance that we can get. We have intense emergency material needs like water, like non-perishable food, like diapers, like hygiene products. So all of those donations mean the world to those of our people who are struggling.
I want to thank everybody for coming together in this time of crisis. Please continue to stay with us, continue to pray. We'll build on God.
And this is Henry Red Cloud. He owns Red Cloud Renewables, which is it's Lakota-owned, Lakota-run renewable energy manufacturing. And he got flooded out. And you know, this is an indigenous man whose land was stolen from his ancestors, who has been heavily impacted by climate change while he's trying to promote renewable energy, which is a solution to climate change. And it's heartbreaking.
Morning. We're here on our 9th day now, flooding down here. As you can see in the background here, a house is totally lost. It's underwater. I'm guessing about 6 to 8 inches, maybe 10 inches inside the house. It's one of the houses here on a compound here at Red Cloud Renewable. A total of 5 houses have got submerged like this. Everything has been lost, and it's just it's a terrible time for us here, you know, today, as well as numerous people here on the Pine Ridge Indian Reservation here. The whole community, the township, everything, it affects everything. The family here, Avery, my son, his family, his 3 daughters, and pregnant wife once resided here, and they can't access anything in there. They were evacuated out 8 days ago when this flooding came in.
It's deep, Hondo. That's why we can't go even to the house. Can't go there.
I imagine things are all lost in there.
We lost homes. We're going to have to bring homes back here again to number 4. For our family, you know, we need to know how all the other families are doing out there too. We haven't heard from some of them. So many people affected, and people got sick and died from this too, you know, because they couldn't get out of their house and get to a safe place to be rescued.
We're going to continue on. We're going to rebuild. We're going to rebuild stronger, and we're going to continue on bringing clean energy forward so we don't have this happen.
Thank you for helping and donating to us, because I know we're going to need help.
Being the elder here on a compound with my family, my wife, my children, my grandchildren, it really devastates me. It makes me feel really bad to see this, to see all the flooding and everything that's happening here. But, you know, nevertheless, with your support and our partnerships, we can overcome this, and we can make sure that nothing like this happens ever again to us, as well as other people too.
So if you are interested in knowing Henry or you know, helping him out, you can contact him through us, or you know, you could reach him through his PayPal. We've done some work with him as well. And so here he is again, Henry Red Cloud, on the headline of an Intercept article. Trump pushes a new pipeline permit as floods devastate Native American tribes. He's trying to revive Keystone XL and push it through their lands again. And not only that, he just signed something yesterday. He signed an executive order to take away states' rights to block pipeline construction. So he's making it harder for states to do the things that the Lakota people did at Standing Rock and try to stand up to the pipeline. I mean, yes, that was ultimately unsuccessful, but...
Are the states fighting that now?
Well, they better be. This was like last night that I saw this, so they should be fighting it because it's a complete overreach. Anyway, so now we can start to talk about, or now that we've seen the current effects of climate change and how devastating and heartbreaking they truly are, we can start to really think about the future impacts in the proper context. Because these aren't just charts and figures and numbers, these are people's lives. These are people's homes and their grandchildren and their businesses. And so when we're talking about predictions, we have to talk about how we make predictions. How do you predict the future? Last time I used the example of gravity acting on a falling pen to demonstrate the inevitability of climate change. But how did you know that the pen was going to fall and hit the table when I dropped it? I mean, how did this pigeon know that the bus wasn't going to hit it? You've seen pens fall before. You've seen things fall before. The pigeon's probably seen a bus before, and it's like, it's 9:30. It's coming around the corner. I'll be fine right here. I mean, that's a joke. But you're creating a conceptual model in your head based on prior experiences that you've had with your environment around you, with reality. So taking the idea of the pen again, if you were to measure how fast the pen fell, how far it fell, the weight of the pen, different things like that, you could attach numbers to your conceptual model of, like when I drop the pen, it falls. That's your conceptual model, but you can attach numbers to that. You can create a numerical model. And with a lot more testing and poking and prodding and a little bit of coding, you could program that conceptual and numerical model into a computer and have it calculate the exact trajectory of a pen that was falling anywhere in the world of any size, at any trajectory. And so that's the power of models, and they're based off of things that we can see and that you can measure, and we refine them over time, and that's what climate scientists do when they're building a climate model. Is they take things like the planetary orbits, the Milankovitch cycles, which we talked about last time, the eccentricity of the planet, its ubiquity and precession. They take things like the transmittance of electromagnetic radiation at the top of the atmosphere. This should look familiar from last time. We've got the infrared absorption band right here, yeah, and then. They take things like the energy balance of the Earth, this conceptual model, this numeric model. They plug it all together with things like the carbon cycle and other biogeochemical cycles, other ecological processes. So just a lot of different things. They take it and they model it for a square unit of planet. And they repeat that for the entire planet and each layer of the atmosphere, because different layers of the atmosphere behave differently. They model it for layers of the ocean, because layers of the ocean behave differently. So, and models are typically, once they're all built, models are typically spun up by running climate data that we already have through them, to the past. So we start them off in the past and we catch them up to the future and see how well they predicted what we know happened. And once you do that, you get a few iterations, a few thousand, a few million, whatever, then your model's starting to look pretty good because it can predict what actually happened in the world. And so then you can say, well, if it could predict what happened in the past, it could probably predict what's going to happen in the future, right? And so these things have developed over decades now, and they started off, pretty simplistically. If you take the idea of a falling pen, and then you turn it into something that you could calculate the trajectory of rockets around the planet. It's the same ideas, it's the same model of gravity. And that's what these are. This is basically showing from the mid-1970s up until the fifth IPCC report, which came out in 2013, 2014. They've added a tremendous amount of complexity to these models. They're getting down to land, ice, atmospheric chemistry, dynamic vegetation, et cetera, et cetera, et cetera. So these models are good. They're really good. And we can predict a lot of things. We can make a lot of very accurate predictions that we've measured against data that we've collected about the climate in the last 20, 30 years, whatever. But there's some things that we can predict better than others. Because it's a more direct consequence of an increase of greenhouse gas emissions, right? So things like a decrease in the amount of extreme cold days. I mean, you know, as the planet gets hotter, it's going to have hotter days too. And that probably means more drought as things get hotter, and you know, maybe more boom and bust rainfall cycles. But you know, things like severe convective storms, wildfires, these are things that we know are going to happen with climate change, but we just can't say exactly how far. You know, we can't say there's a 27% chance there's going to be a 500-year wildfire in California next year. We can't say that with with extreme certainty, but we do know that wildfires are linked to climate change. All models are wrong, but some are useful. And that goes for beyond just climate models that we're going to be talking about today. It goes for every model that you carry around in your head, consciously or unconsciously, about other people, about the way that gravity works or the way that pens fall. And so we have to, in climate science and just in our personal lives, in order to have a useful model that can accurately predict reality, because that's what we live in, right? We need to examine the underlying assumptions. You need to verify it against real-world data, and you need to be constantly iterating that process of adjusting your model when new information is found. So our models are extremely good, and as computing power increases and gets better, and a bunch of smart people continue to think about this problem very, very hard, these models are just going to get better and better. So the information that I'm presenting you today, a lot of it is several years old because the IPCC reports take several years to come out. They take about 6 years to write on average. So keep that in mind as I'm showing you all this, because some of these data have changed since they came out. And I'll be talking a little bit about that as well. So once you get your model built, you need to have your inputs. You need to get the ball rolling, so to speak. And so with these climate models, climate scientists, and particularly those at the IPCC, have settled on these what are called relative concentration pathways, RCPs. And that's just different scenarios of carbon emissions. So, say we were to basically immediately start ramping down our carbon emissions tomorrow. Never going to happen. But if we did, this is what our carbon emissions would look like over time. If we were to do a pretty good job, this is what they could look like. If we did kind of a moderate job, we could maybe end up here. Business as usual is the red line. And so that's what would happen if we just kept doing what we're doing, pumping pipelines through indigenous territories, pumping out tar sands from Canada, et cetera, et cetera, et cetera. Building entire global military industrial complexes to protect our oil interests. Think about all the money we could save. And so this is a huge table, but I just wanted to concentrate your attention on this particular section here. So this is a breakdown, and you can study this. So these lectures are going to be on the syllabus. The first one is already uploaded. This one will be uploaded after today. So you can take a look at this in more depth. It's also available on the IPCC reports. But basically, this is showing that with a CO2 concentration of 450 parts per million, we have less than a 50% chance of staying below 1.5 degrees C by the end of the century. So the very fastest we could possibly do, where we're cutting out our carbon emissions tomorrow, we may still not make it under 1.5 degrees C. But we have to try, because it scales, right? It's proportional. The more carbon and other greenhouse gases we pump into the atmosphere, the worse climate change is going to be. So just because we don't have a great chance of staying below 1.5 degrees C warming doesn't mean that we should just give up, because we've got a pretty good chance of staying below 2 degrees C warming, and that's still extremely significant. But we're at 411.91 parts per million of CO2 right now. So compare that against the 450 that we need to have a good chance of staying below 2 degrees C. We're pretty close. And in fact, a lot of these models account for that. They account for an overshoot. So, and that's kind of one of the flaws, you could say, with these models, is that they do kind of allow for this savior technology or something. We figure out something that we can start to pull carbon out of the air. And that's probably, hopefully, if we can do anything about it, soil carbon sequestration, because that's just kind of the best and cheapest option. But we'll see what happens. So now that you can understand how these predictions are made, we can start moving into the actual predictions, because now you can have some confidence in how these numbers are arrived at. So first, we're going to be talking about kind of the most basic thing that we can predict with climate change, is that things are going to get hotter. And so here's a similar graph to the last one, except this is the change in radiative forcing. So that's that energy balance of the Earth, right? And as you put in more energy, you have to equal it out with the amount of energy that comes out of the Earth, otherwise you get climate change, right? We went over that last time. So this is showing what the radiative forcing changes is going to be at the top of the atmosphere under the different conditions. And it's, as you can see, very, very high under the business as usual scenario, so we should probably avoid that. And then that results in a global surface temperature change, we'll wait for that to go away, of anywhere from 6 to 12 degrees centigrade, and which is like, just multiply that by 1.8 for Fahrenheit. But another thing to really notice about this, this graph here, especially this bottom one, is that these fuzzy bits, the uncertainty associated with each prediction, gets larger and larger the more greenhouse gas emissions we put out into the atmosphere. So we have a pretty good idea that if we cut our carbon emissions right now, we'll be safe, we'll be good. But the more carbon and other greenhouse gases we put in the atmosphere, we just don't know what's going to happen. We're pushing the system past a point that we've never seen before. Well, or have we? We'll talk about that in a second. But these temperature changes, and I alluded to this last time, they're not geographically distributed evenly across the globe. They're concentrated primarily at the poles, and so what this picture is showing are the different scenarios here. So the RCP 2.6, so the lowest one, the medium one, slightly higher, and then the highest one going down, and increasing in time as you move from left to right. So 2065, 2100, 2200. So over the next 200 years. This is showing the temperature increases predicted for the planet. And one thing you can see down here in the business as usual scenario is the Arctic gets really hot. It's like a 13 degrees C increase, which is, I don't know, something like, 25 degrees Fahrenheit about there. That's really hot for, like the Arctic Circle. It really shouldn't be that warm, and that has major consequences for, nutrient cycling, ocean currents, air currents, just all the life that lives there as well. And you can break it down even further because we can do finer and finer scale models as our computing power increases, and we can shrink that grid on the planet, when we're building our models. And so we can actually do it, now for, just one part of one continent, for example, the United States. And so here's the predicted temperature changes for the early 21st century and the late 21st century under the two different scenarios, the kind of medium one and the business as usual. And it gets hot. It gets about 8 to 9 degrees hotter throughout most of the United States by the end of the century under the business as usual scenario. And we can break it down even further now because our computing power and our satellite technology has gotten really good that we can actually break it down by almost like a county level basis about what's going to get hotter. And so this particular one is showing temperature changes that have already happened, but we can model these out as well. So Southern California is warming up a lot faster than Northern California, and that's a function of the environment that's there. Southern California is largely desert. Northern California is mostly forest. So they have different albedos. They have different hydrogeologic cycles and things like that. And so those types of microclimates are going to be really important when climate change accelerates. Yes?
Do these models sort of account for, because you said the Earth goes through natural cooling and warming cycles?
Yes.
So do they, I guess, take into account sort of maybe some natural climate change in the next 100 years?
Absolutely. Absolutely. So the last time, I don't know if you remember, we were talking about radiative or climate forcings. So things like solar irradiance, volcanic eruptions, solar like sunspot cycles, things like that. So those are all, and the orbital mechanics of the planet as it moves around the sun and wobbles back and forth. So those are all things that we know and we understand very well, and they are absolutely incorporated into these models. So, I mean, these things are, I just want to impress upon you how incredibly complicated these things are. They take teams of hundreds of people to build and to understand and to to work with. And yeah, so chances are, if you can, think of something, one of these people have thought about it as well, which I find reassuring. Yeah.
Last class we talked about the jet stream and how it's going to become
Yes.
heavier.
Mm-hmm.
In like a previous slide, you showed like the Michigan area warming up. Is that also with the jet stream just going to create more
Like up here?
Extreme, more extreme temperature changes, or is it heating up?
Yeah, so we'll talk about ocean circulation in a little bit later today, but just as a preview, it causes warming and cooling because ocean currents carry heat around the planet. And so if you break down those heat conveyor belts, then your heat isn't able to be distributed as evenly throughout the planet. So it's a little bit of both. And in fact, you can kind of see that the southeastern United States has actually been observed to be cooling a little bit because it gets hit from that Gulf Stream, which comes down the coast and kind of wraps around the Gulf of Mexico there. So as the planet heats up, it's not just uniformly getting hotter, right? It is geographically varied. It varies based on microclimates, but it also varies based on time. And over time, the number of warm days is predicted to increase. And that's just, obviously, if the days are going to get hotter, then they have to get hotter sometime during the day, and it's probably not going to be at night when the sun's not shining. But also the number of cold days decrease. And this is, again, something that you would predict, just common sense, but it has really important implications for things like agriculture, for things like, any plant or animal that relies on seasonal cues. When those seasonal cues shift, then the species are impacted. They may not be able to catch up. They may not be able to migrate in time or in space to match up what they need out of the environment with the changes that are happening to it. And so as the number of warm days increase, the number of cold days decrease, the amount of moisture in the soil is also going to change because it's related to how hot it is, also how much it rains, which is also changing. And so these are the 4 different scenarios, from low, medium to high, across the whole planet. You can see that soil moisture, the next 100 years under the highest emission scenario is going to drop precipitously for large amounts of what are now forests. So like a lot of the rainforest is going to have a lot less soil moisture, which means that plants can't grow as much. All the organisms in the soil that rely on that moisture to live and to do what they do that is so important to the environment are not going to be able to function as well. And as it gets hotter, you have human impacts as well, like melting pavements in India. You have Indian farmers committing suicide because their crops have completely failed and they have no way of supporting their families and they are hopeless. India has seen a massive skyrocket in their suicide rate because of the droughts and the heat famine, the famines and things like that have resulted. And this is drought in Namibia, desertification, Nigeria, and then the second largest lake in Bolivia, Lake Papua, has disappeared. It's just gone. It disappeared over about the last 50, 60 years. And, of course, the fishing communities that rely on the lake, the fish in the lake, they just have nowhere to go. What do? Where do they rely on? They just have to leave. They have to become climate migrants, which is something that it's going to happen to a lot of people. And it's not just people that are going to be climate migrants. It's also things like trees. You wouldn't think of, a tree being a climate migrant because it can't move, but over time, species distribution changes, and they often change in response to environmental conditions. But when they happen, when environmental conditions change too rapidly, plants and animals aren't able to keep up a lot of the time. And so what this is showing, this is from the Canadian Forestry Service, but it shows the current climate suitability zone of aspen trees. So these are, a really important tree for a lot of Canada and United States forests ecology. Over the next 100 years, under the business as usual scenario, basically all of the aspen in the United States, in the continental United States, is going to disappear. It's going to die off because it's going to get too hot. It's going to get too dry. And even a lot in Canada, it's going to continue to shift. And this isn't just like, a few people getting up and walking. This is an entire ecosystem getting up and moving. And can it do it fast enough? What happens to the things that can't move with as the trees move? Do they die off? What happens when the trees move to a new place, or they're in a place where the climate changes, it gets hotter, it gets drier, they get stressed, and then they become more susceptible to things like bark beetle, which is a huge problem for California and a lot of the continental United States, because it kills trees and it leaves them looking like that, which leaves them, perfect fuel for massive, intense wildfires, which are way crazier than they've been in the past because of there's so much more fuel available. And it's not just trees; it's things that live in the ocean. They're a little bit more mobile than trees, of course, but and because of that, you can track their movement on smaller timescales. And that's exactly what this is showing here. So this is a bunch of different species from around the globe, and groups of scientists have been tracking them, and they can see that just all these different species are moving in response to changing environmental conditions due to climate change, including things like frogs, which are experiencing a massive die-off right now. And they're kind of our canary in the coal mine. They're dying off due to a chytrid fungus, but their susceptibility to the fungus and the fungus's proliferation may be linked to climate change, and to the stress that the frogs are dealing with as things get hotter and drier, because they're amphibians. They need moisture. They need cool, damp places. So I talked a little bit about the changing cold days affecting seasonal patterns, and we're gonna and changing rainfall patterns. And how does that work? Well, so as you get warmer atmosphere, you get more evaporation. And as you get more evaporation, you get more clouds and rainfall and things like that. And so that causes shifts in where rainfall occurs around the globe. And if you don't have rainfall for a few years, you are going to drought, and then you can't grow crops. And your entire population has to move. And that also affects the distribution and the frequency of major storms like cyclones and hurricanes. And so what this is showing is the frequency of tropical cyclones. So here's the little legend here. So number one, so the first kind of column here is all tropical cyclone frequency. So how many cyclones and hurricanes are happening in a year. The category, or the frequency of category 4 or 5 tropical storms, so hurricanes, are they getting more frequent or less frequent? The lifetime maximum intensity, how intense is each storm on average getting? And then the rate of precipitation, so how much rain is it dumping? And that's something that's really important, as we saw with Hurricane Harvey in Texas. And as you can see around the globe, it's interesting that the number, or the frequency of major storms is actually decreasing. It's predicted to keep decreasing, but we're going to have bigger, more intense, more damaging storms. So they have more rainfall, they're more intense winds, but they just come less frequently. So, is that a good thing or a bad thing? It's probably a bad thing, because it's much harder to recover from a big storm than it is from a smaller storm, even if the smaller storm only comes every other year. And with those storm surges come flooding. And so this is a chart showing the predicted changes in flooding frequency around the world. And so what it's looking at here is a 100-year flood. So it's the magnitude of flood that occurs on average once every 100 years. Is that particular size flood, is that happening more frequently or less frequently? And the blue is showing that it's happening more frequently in a lot of the places around the world. And in fact, 100-year floods are dropping to every other year in some places, and they will continue to drop. And with changing rainfall patterns and flooding patterns and things like that, you get changes in groundwater recharge. And I think a lot of people aren't really aware of how important a resource groundwater is, but basically we wouldn't have agriculture in California without our use of groundwater. We use a massive amount of groundwater, and California kind of feeds the nation. The vast majority of groundwater that we use for agriculture. So a lot of it we use for pumping out oil and gas, or we pollute it when we pump dirty water from oil and gas extraction back underground into the aquifers. And then we use a small amount of that for drinking. And so you can see that a lot of the aquifers around the world are at high risk of depletion due to climate change. And that's just because they're not being recharged, or people are drawing out the water faster than it can be used because of increased evapotranspiration rates in their fields. And the plants respire faster. They suck water out of the ground faster when it's hotter. So you have to water them more. And also impacting agriculture are changes in seasons, right? So I alluded to that earlier, but things like apple trees, or they need a cold snap, right? They need some trigger that lets them know on a genetic level it's time to start flowering. Spring is sprung, and I need to get out there. And those signals are changing for plants and animals, and that's what this is showing here. This is predicted adult mortality rates, birth rates, and maturation rates of different animals and plants around the world. So in temperate zones, in Mediterranean zones, and tropical zones. And basically adult mortality rates, as temperature increases, so it's going up here, as temperature increases, adult mortality rates will increase, so the adults will die more, the birth rate will go down, and the rate at which the species matures will go down because more young will be dying as well. And why does that happen? Well, I mean, for some of the reasons that you can imagine, right? If you are a migratory bird, for instance, and you are flying in from Mexico to California, and you're hoping for a nice, tasty caterpillar on one of the trees, but for your young, but that caterpillar has already turned into a butterfly and flown away because it got the seasonal cue here, 2 weeks earlier than it did 20 years ago. And now you're there and you've laid your eggs, and your hungry chicks are on the way and you have no food for them. What do you do? Well, what do? You can't carry the egg. So these things have cascading consequences across things that you couldn't necessarily picture at first glance. So next, the melting of the ice caps. And this is something that's very important when it comes to sea level rise, obviously, but there's a difference between sea-based glaciers and land-based glaciers, and I mean, obviously, the difference is right there in the name, but they have major differences when it comes to things like sea level rise. And so the difference between the sea ice and the land ice, obviously, is where they're located, but sea ice doesn't contribute to sea level rise. And it's the same reason that when you put ice in a glass, the glass doesn't overflow when the ice melts. It's because the amount of mass that the ice is taking up has already been displaced by the ocean. It's already floating. So once it melts, it's fine. But it's these land-based glaciers that are not already sitting in the water, already displacing their mass, that when they melt and get into the ocean, then they cause very rapid sea level rise. And in fact, they can be affected by the sea ice because they're often connected. So the land-based glacier will flow into the sea. So glaciers, even though they're ice, they flow. They just flow very, very slowly. And so they can flow off the land and kind of form continuously into a sea ice. And that sea ice can get undercut as the water gets warmer. And that's a hypothesis that's kind of gaining traction. It's the marine ice cliff instability theory. And it's basically saying that as the ocean warms up very rapidly due to anthropogenic climate change, it's hollowing out the undersides of these glaciers and causing them eventually to collapse. And if you break off a big piece at the end, then the rest of it starts to flow faster because it's encountering less resistance in front of it. And so these types of things that affect the sea ice can actually also affect the land ice. And so here's a prediction of what sea ice is going to be around the Arctic in 100 years under the different scenarios. And so this is the Arctic Circle here, and the gray and the white are the ice. And so you can see from these graphs here that the September sea ice extent, so that's the amount of sea ice that's there at the end of summer. So basically the lowest amount of sea ice all year. By 2100, under the high, business as usual scenario, there will be no ice in the Arctic in the summer. And that hasn't happened for as long as humans have been around, and it certainly hasn't been the case since countries have been around, and countries that want to use shorter trade routes, shorter shipping routes, and so they're probably going to try to start shipping through the Arctic, places like the United States, like Russia, like China, because we're all right there. And so it has interesting political implications as well. It also has implications for the albedo of the planet, because as I mentioned last time, ice is more reflective to light than the underlying soil or the plant material that grows on the soil. And so that leads into a feedback loop that we discussed last time of the Earth becoming more absorbent to the energy from the sun as the ice melts. So it heats up, the ice melts, and it heats up more, and the ice melts more. And you can see this here with the cover of the snow extent change, and also, more importantly, the permafrost area. So permafrost is just permanently frozen soil that's typically located around the Arctic, and it's basically expected to drop to almost nothing under the business as usual scenario by the end of the century. And why that is such a big deal is because permafrost is one of the biggest stores of carbon in the carbon cycle. And it stores it in dead tissue, leaf material, just gases that are frozen in the soil, frozen in the dirt. And as that dirt melts, the things decompose and all that gas gets released. So we really need to keep that from happening. And it's estimated 1.7 trillion tons of carbon in the form of frozen organic matter locked into the permafrost. And of course, that has an impact on the native indigenous people that live in the Arctic as well. And so this is just a short video showing the impact on Inuit culture.
This is the only road linking Umujak to the rest of the world. Since the surrounding terrain caved in, the tiny village in the far Canadian north seems even more isolated. Experts say the collapse is due to the melting of permafrost in the subsoil, a phenomenon that's accelerating as the atmosphere warms up. Climate change may be an abstract concept for many, but for the 430 residents of this Inuit village, it's a daily worry.
Just across the river, there used to be tons of caribous, like hundreds. But there's no more caribous. We can hardly see them anymore.
No, the salt water is a lot warmer, and the fish go deeper sea. So we're getting hardly to get fish now.
It's become difficult to hunt and fish. Winters are mild and summers often hot. This subarctic zone is heating up twice as fast as the rest of the planet. Lukasi, a local teacher, says his grandmother saw it coming.
When I was a kid, my grandmother used to tell me someday there will be no snow. I didn't believe what she had told me, that some predictions had already come true.
There's still snow in the winter and the sea still freezes over for months. But with higher temperatures, the subsoil has become unstable, which makes building houses hazardous.
In the past, we were building pat and built the house right away, but they were going down, crack in the building. Right now, we learned that we discovered to make a house pack at least 1 year before they built the house on top.
Life has already become harder for the Inuits, but scientists predict that ongoing climate change will make it worse still.
We'll see what happens in 10, 15, 20 years. There will be more tree growth, and that may have a real impact because there will be more flies and fewer small fruit available. The local population depends on small fruit a lot.
The Inuits have always managed to adapt to the many changes in their environment. But climate change may be the biggest challenge yet, and nobody knows whether this time it's one change too many.
Yeah, so they're having a lot of troubles there with land subsidence, as they mentioned, but also with things like sinkholes, because as the permafrost melts and things inside start to decompose, they release that gas, and that gas goes up. And it used to be solid material in the ground, which is now a sinkhole. So we talked about the melting of glaciers impacting sea level rise, but that's not actually the only thing that does impact sea level rise. It's actually mostly caused by just the water itself heating up. Things expand when you heat them up. They also glow. Lots of exciting things happen when you heat things up. But as the water expands, or water heats and it expands, and it actually makes the volume of water larger than all of the ice melting. And you wouldn't, think about that. And it actually changes in a non-linear fashion because of ocean cycling. So the ocean currents mix the deep ocean and the surface ocean very slowly. It depends on where you are, but it could take thousands of years. And so that also includes heat transfer. So right now we've expanded the upper portion of the ocean. But then later, we're going to expand the lower portion of the ocean as all that heat that's now in the upper part goes down lower. And this is showing a breakdown of sea level rise predictions and the different components. And you can see that the red is the thermal expansion, and that's the one that's on top, except for the aggregate of the sum of them all. So under the business as usual scenario, by the end of the century, global mean sea level is predicted to rise, anywhere from 0.6 to 0.8 meters. So, 2 feet approximately. But this was the IPCC's old prediction. And unfortunately, and it's actually, I just wanted to mention real quick, it's not, funnily enough, the sea level rise is not geographically distributed evenly across the planet. You think, well, water will just flow, but actually there's parts of the water that are hotter and parts that are cooler, and those expand at different rates, as you now know. But even skeptics of the theory that I mentioned earlier, the ice shelf collapse theory, agree. Our understanding of sea level rise is rapidly growing more ominous. In its last major report in 2014, the IPCC projected that oceans could rise 2 feet by 2100 if greenhouse gas emissions continue on a worst-case trajectory. That's what I just mentioned. That number will almost certainly worsen in the IPCC's next report, which is due in 2021. We are facing sea level rise that is obviously going to be higher in the mean than what the IPCC's fifth assessment report showed. So, 2 feet of sea level rise may not sound too bad, but it's actually going to be even worse. And we don't know exactly how bad it's going to be because we can't predict exactly when all these ice shelves are going to collapse. But when it does, this may be what happens to Central California. This is the San Francisco Bay under 1.5 degrees C of warming and 2 degrees C of warming. And you may not recognize it, but this is Stockton and this is Sacramento. And the reason that there's so much flooding is because of the Sacramento River Delta is actually a little bit below sea level. And so when you have even just a little bit of sea level rise, you have to do a lot of work to build things like dams and dikes to prevent basically a lot of the Central Valley from flooding. All the way, can you imagine having, oceanside property in Sacramento in, 100 years? Well, maybe. But it's not just, the sea is not just rising and it's not just getting warmer, it's also the properties of the ocean itself are changing. The salinity, the pH, the temperature. Oh, yeah.
Well, like in that last example, would it be, saltwater all the way in Sacramento? Because the delta is largely fresh water.
Well, yeah, so right now, the river is flowing one way, and it's carved out a channel that's below sea level. But as the sea level rise, it will fill up that channel with seawater. And that will create an estuary. That's what an estuary is. It's a drowned river mouth. Anyway, so did that answer your question? Yeah. Okay. So temperature will change, but dissolved gases and nutrients and salinity will also change. And then we're also just going to talk really briefly about ocean currents because it's really important. So this is a figure from the IPCC report that I liked, and I just wanted to throw it in here. But basically, it shows an overview of the entire process of changes in the ocean, from burning fossil fuels to what do policymakers do. And you can check this out on your own. But we're going to be kind of jumping in right here, and then you can think about all this stuff for your first writing assignment. So. We know that the ocean's getting hotter, and we know that the pH is dropping. But what about all the other stuff? How is nutrient supply affected? How is visibility affected? Well, as climate change progresses, there will be more dust storms because there will be more storms. And as that dust settles on the ocean, it will block out the light, and it already does that. It will just increase the amount that will do that, and that will decrease the photic zone of the ocean, the amount the layers of the ocean that light can actively penetrate. And so that's where you get things like phytoplankton. That's where you get the most kind of productive waters, is in that zone where light can penetrate. And if you shrink that zone, you have immediately just shaved off, 10% of the ocean's primary productivity, or at least the surface oceans. And in addition to that, the amount of oxygen in the water also drops. And this is something that you can measure. I mean, if you go onto a scientific supply website and buy a dissolved oxygen probe, you can measure this. But with a pot of water and on your stove, you can measure that the amount of oxygen that's stored in water decreases as that water heats up. And that's just because the water molecules are moving faster. They wiggle and jiggle more, and they bump out the light gas molecules. And fish don't like that. Fish like oxygen. We like oxygen. They like it too. And a lot of other marine organisms like oxygen, and in fact, they rely upon it just as we do. And when oxygen levels drop too much, they suffocate. They suffocate in the ocean, and it's kind of a weird concept to think about. But it has major impacts on, especially juvenile fish species. Yes.
What was the name of the process that you just said right before this one, where the dust settles on the ocean and it blocks out the light?
Oh, I didn't mention, I don't think I gave it a specific name, but I did refer to the top level of the ocean as the photic zone. That may be what you were talking about. This just means photic, like it's light, so it's the light area of the ocean. And so, the oxygen levels of the oceans are dropping, and they will continue to drop, and that has serious implications for especially juveniles who are more susceptible to harsh environmental conditions. I went through this little thing last time, the climate chemistry 102, that carbon dioxide plus water equals carbonic acid. And that means that the oceans are getting more acidic. And they're getting much more acidic. And in fact, the amount of acidity in the oceans is something that takes a really long time to change. Because it has a lot to do with ocean mixing patterns and all the buffers that are in the ocean that keep it at about 8, pH of about 8. So, neutral water is 7, ocean water is 8 because it has a lot of stuff in it. It has a lot of dissolved ions and things that buffer that pH to be constant. And so, because it has all those buffering things, it will take a long time to change the pH. But once it does start to change, it will change rapidly, and it will continue to change for a long time. And it's one of those things that is also dependent directly on the amount of greenhouse gases in the atmosphere. So in the northern hemisphere, the water will be more acidic because most of the greenhouse gases that are being emitted are coming from people who are living in the northern hemisphere mostly. And that has a lot of impacts on organisms that make shells and skeletons out of carbonate ions, because there will be fewer available carbonate ions in the ocean. So things like mollusks, crustaceans, cold water corals, and warm water corals are all predicted to suffer massive negative impacts due to the increase or the decrease in the ocean's pH. And for something like corals, who have kind of a complex life cycle and complex physiology, this is something that is extremely devastating. Because coral, as many of you know, I'm sure, are symbiotic organisms. So the corals, when they get stressed, they're symbiotic algae that live within them. They can leave. So the corals build a calcium carbonate skeleton that they live inside, and then they also build little rooms for their algae friends. And the algae friends, they get sunlight from the atmosphere, and they produce sugars and other compounds that the coral eat and can survive off of. Coral also filter things from the ocean, but it's kind of a supplementary thing. But they need the algae to live. And the algae get easily stressed by things like temperature changes and dissolved oxygen changes, salinity changes, pH changes, and they leave. They can actually, the algae can get out and leave from the coral, and they swim away. And the coral doesn't die immediately, but it will die eventually if the algae don't come back. And so you see, you've seen bleached corals like this up here. That's what happens when the algae leaves. But that coral is still alive because it's white. It turns to black when it really dies. So I kind of got to go a little bit faster now because of all the technical difficulties. But essentially, salinity is going to change, and it's not going to change evenly. And if you've ever tasted the seawater on the East Coast, you know that it's a heck of a lot saltier than the water that we've got out here, and that's partially because it's warmer. And warmer water can hold more things. It can hold more, we can hold more salts because it dissolves them more. And that has implications for things like fisheries, because fish are dependent on all of these conditions, you know, dissolved oxygen, salinity, pH. And as fish population shifts, fishing populations will shift. And you know, that introduces a whole new class of climate migrants, people who are chasing the fish. You know, people who are mobile, they have their boats. You know, maybe, you know, there's a lot of fishing communities that kind of live on or near their boats and, you know, are able to follow these things. And, you know, so that's, you know, an interesting way to correlate climate migrants with, you know, species migrations. And not only that, but it affects the phytoplankton production in the water that the fish rely on. You know, the phytoplankton are the basis for a lot of marine food webs. You know, things from, you know, like some types of whales eat them. A lot of fish, zooplankton eat them. And this is a measurement of the primary production that's done, or so the photosynthesis that's done by the phytoplankton. We can measure that from space, and then, you know, we can take those measurements and use them to build a model that we can predict in the future. As you can see, there's predicted to be a lot of changes in primary production, which means that phytoplankton populations will be shifting and some places decreasing a lot. And that has an interesting consequence that you may not be aware of, but it changes cloud cover because phytoplankton create clouds. Some types of phytoplankton, a very common one, they produce something called dimethyl sulfide, DMS, which decomposes in the atmosphere to hydrogen sulfide, or sulfuric acid, and then to a sulfate ion, which flies around in the atmosphere and attracts water molecules to it. And those water molecules turn into clouds. So phytoplankton, these little things living in the ocean, create all the clouds, basically, not all the clouds, but a lot of the clouds on the planet, especially over the ocean. And so if you take away the phytoplankton, then you don't get clouds. And if you don't have the clouds, then you don't have the rain, and you don't have the albedo, the reflectiveness that clouds have. And so the planet gets hotter. And this is just a chart showing how cloud cover is going to change. And it's not just the phytoplankton, you know, of course, it's also the ocean currents and the atmospheric patterns. Speaking of ocean currents, this is a picture showing global ocean currents. And we're going to particularly focus on one part. Let me get my pointer back up here. One aspect, or one part of this. This is in the northern Atlantic Ocean. It's called the Atlantic Meridional Overturning Circulation, or the AMOC. And this is responsible for keeping a lot of the northern hemisphere, especially around the Atlantic, habitable. So it keeps, you know, places like the northern United States and, you know, England and a lot of Europe warm and mild. You know, it's responsible for the English roses in the wintertime and things like that. But this current is driven by changes, or by differentials in salinity and temperature and in the ocean water. And so because they have different densities. And so hot water is lighter and it rises to the surface. Cold water is denser and it sinks. And so just from that very simple relationship, you get this entire pattern, this entire circulation of the world's oceans as it redistributes heat around. And this, because it's based on temperature and salinity differences, it's very susceptible to things like ice caps melting, right? And this is a climate impact that would basically affect the entire world if this current collapsed due to the intrusion of fresh water from glaciers, like right here on Greenland, right outside, right next to the current. And if that current collapses, I mean, you can see it's one of the major drivers for the entire oceanic current system. And it's a low probability but high impact climate change, effective climate change. But the IPCC has projected that it's probably not going to happen. But the IPCC is probably wrong. And because recent research has come out that has shown definitively that the AMOC has already weakened in the last 50 to 60 years by 15%, which is, you know, I mean, this is percentage decrease as well. So it's basically what the IPCC has predicted for the next 300 years. It's happened in the last 60. So we don't really know what's going to happen with the AMOC. Stay tuned. But one thing that I really loved about this is that scientists and their acronyms. So the program that discovered the 15% decrease in the AMOC is called the Overturning in the Subpolar North Atlantic Program. Oh, snap. And they did find something that was very shocking. Anyway, so we're getting close to the end here, and I wanted to leave just a few minutes for questions, although we'll also be having office hours today. But I just wanted to get really quickly into a brief discussion on feedback loops and tipping points and mass extinctions in the past. So you've seen this slide last time, and we were talking about carbon sinks and feedback loops. And so basically, I walked you through what happens when you burn fossil fuels. Well, you get more carbon in the atmosphere, but when the ocean heats up, you get more carbon in the atmosphere. When the soils heat up, you get more carbon in the atmosphere. When methane clathrates melt, you get more carbon in the atmosphere, et cetera, et cetera, et cetera. So these are the loops that drive up greenhouse gases in the atmosphere. And these loops will keep driving us until, hopefully not, but I mean, most likely, we reach a tipping point. And tipping points are, tipping points are basically a point which is very hard to get back from, right? And when you're talking about it in the context of climate, it's things like the melting of the Greenland ice shelf. How do you, once that ice melts, how do you pick it back up and put it back on the land? You can't do that, by hand, or it would take thousands of years, probably more than that. How do you get the Amazon to come back once it's all chopped down? You remember, I told you that the rainforest actually creates the rain by increasing the amount of evaporation that happens over the rainforest. So the rainforest literally brings the rain, and when you cut down the rainforest, you don't get as much rain. And so that's something that's a tipping point for the Amazon. And these are all the list of tipping points. There's more that aren't included here. People have come up with lists of 100 or whatever, but a lot of them are kind of just pearl clutching type stuff. And this is a table that you can go through on your own as you're reviewing the slides. But this just talks about, is it an abrupt transition? So is it something that's just going to happen overnight, like Day After Tomorrow? I don't know if you remember that movie. That was the collapse of the AMOC. That was the driver there. I mean, there was obviously a dramatization. It happened extremely quickly, and we're not all going to get chased down library hallways by freezing ground or whatever. But it's a very abrupt transition, and it's probably irreversible. But they say it's very unlikely, but we know now that that's probably not true. So, but these are all tipping points, and it's just not something that I'm trying to scare you about, but it's things that are really important to keep in mind, because the higher we get, the closer we get to one of these tipping points, or maybe more of these tipping points. And so we really, really, really need to keep our carbon emissions low, because we might run into another another mass extinction. There have been 5 mass extinctions in Earth's history, and each one of them has had a certain cause, but at least 3 of them have been related to climate change, rapid climate change. And that's either been through volcanic activity or through weathering of rocks. Sometimes it's gotten hotter fast, and sometimes it's gotten colder fast. But rapid climate changes cause mass extinctions. And some scientists went and tried to plot the relationship between carbon cycling in the ocean and mass extinctions. And what he found is that a lot of the times carbon pulses in the ocean tend to fall upon this line, but it's which is time over which change occurs and relative change in ocean carbon mass. So the amount of carbon in the oceans versus how fast it got into the ocean. And most of the time they kind of follow a one-to-one relationship, but if they're above, if the amount of carbon that's put into the ocean happens very quickly, then you get a mass extinction. So this is pretty damning evidence that we need to slow down our emissions as much as possible, because if we put too much carbon in the oceans too quickly, we run the risk of another mass extinction. And when you're talking about the threshold for which that starts to occur, we're almost there. So we really need to slow down. Only one scenario, reducing global emissions starting in 2020, next year, less than a year away, barely avoids the threshold. Other scenarios, hitting peak emissions, then reducing that beginning in 2040 or 2080, or beyond 2100, risks making mass extinction likely. And I just wanted to call out that last sentence in particular because if you recall, I mentioned that the IPCC projections allow for that overshoot and coming back down. So all of the models that I've shown you have been based on this idea that may, may lead us to a mass extinction. And so we just need to work as hard and as fast as we can. And we have to recognize the shortcomings in some of these reports and the science that is coming out so that we can overcome them because we need to. So some of the shortcomings of this report and other reports like it are that they don't come out very frequently. And so policy decisions are made based on old information that may not be the most accurate anymore. And these reports only come out once every 6 years. And so it's really, there's a big lag, and the stuff with the AMOC, that's a major thing that should be impacting policy decisions, but it was not released in the last report, so it's not real. Because a lot of governments around the world only pay attention to the IPCC reports and not, because those are the ones that have been vetted by every country. It's a massive global process, the writing of these reports, and basically every single line has to be checked off by every country. And so that kind of, polishes them a little and smooths out the round edges, like, somebody saying, oh, what if the AMOC is actually, collapsing faster than we thought it was? But that's a scary thing to think about, and that leads you to inherent bias of, oh, well, that's a really big, scary thing to think about, so we're going to think about some other things for a little while. And then eventually you just kind of move away from that whole idea of thinking, and it can really lead to underestimations of the threat level, which really we should be trying to overestimate the threat level so that we come in underneath it, right? Not the other way around. And that also, of course, leads to the politicization of the science. When every single country in the world, all 195 countries in the world are signed on to the IPCC, when every single country in the world has to sign off on a fact, how polished is that fact? How accurate is it still? When it's been passed through hundreds of hands. Anyway, so cats are cute and climate change is scary. So here's a cat. Any questions? Yes.
Have there been any studies that you're aware of or any kind of assays done of the most efficacious low-tech solutions that people who are not part of a GMO,
yes,
or, that's the wrong word, but or whatever those things are, a governmental
NGO
organization or not, that can do an end run around having what appears to be the politicization and the religiosity that follows this whole thing?
My favorite solution, and this is partially because I'm kind of a soil scientist, is soil carbon sequestration. And this is something that's not really been, it hasn't really taken off so far, but it will, it needs to. And California will hopefully be leading the way because California just passed a law regulating compost production. So basically all of the compostable material that goes into landfills right now is going to have to be taken out and actually composted. And so California is going to have a massive supply of compost. And what we should do with that compost? Take it and spread it on all the rangeland and fields that we have to increase the carbon sequestration of the soil. So when you put compost on soil and you treat it right, it will actually sequester that carbon. So you take your banana peel, you throw it in the compost bin, you have coffee grounds in the compost bin, take that compost bin, send it to the composting facility, it gets turned into basically fertilizer, and then you take it and you spread it on your fields, and now that's sunken into the ground for potentially hundreds or thousands of years. You really don't need fancy equipment to do most of the things that we could do to solve the climate crisis. And that's exactly why those are the things that will solve the climate crisis. The things that, I don't know if I put this in the reading, so you should all check out this website, Project Drawdown. You may be familiar with it, but they gathered all of the climate solutions that we could do, and they ranked them on impact. And can anyone guess what the number one most impactful thing is on climate?
Is it being vegetarian?
No. Yes?
Is it the production of animal products?
No. Yes?
Is it getting out of the cars?
No. It's even more basic and fundamental than any of those things. Women's rights. Giving women rights is the #1 solution to the climate crisis. Because it's an entire half of the world's population that can be a productive in helping to solve climate change. That, you know, they do a much better job of explaining it. It takes allowing them to do their own family planning, allowing women to do their own family planning, and educating them. And those are the two most impactful things that you can do for climate change. And I highly recommend that everyone check out that website because it's, this was depressing, and that's very hopeful. Project Drawdown. Yeah, Paul Hawkins. Anyway, so I guess we can, we're just about, 4:55, but we've got office hours right over somewhere. I don't know. I'll be wandering around looking for the room, and we'll see you all next week. Thank you.